Good afternoon, students. We will continue our discussion. So, last day we have seen the layout structure of the NMOS, right. So, these are the mask, one is N plus diffusion, right. This is the polymaterial and we have diffusion contact and some metal. So, metal this in this layout structure, this is the schematic, right, or this is a, you can say that this is not the this is the mask of this layout. Okay. So, this is the metal for this connections, right. All right. So, this is our extended poly. So, let us see the rules. So, for layout you have certain design rules, okay. You have to satisfy those rule checks. So, those are known as the design rule check, DRC. So, what are they? You have a minimum length, okay, minimum gate length for technology to technology, that will be defined, you cannot have less than that. Your poly is overhang, so that mask or misaligned channel does not sort out. Okay. So, this is a by default it is fixed. So, this poly you see little bit overhanging. There is a, this is your active region, right, this is your channel actually, right, beneath this gate your channel is, right. So, if you see this, this is your active region, right. So, there should be a minimum distance between this metal interconnect and the channel. Okay. So, there is a metal rule about the contact, you cannot keep it closer than that. Okay. So, all this minimum rule you have to satisfy. Okay. So, this minimum rule they are specified in terms of lambda, some minimum rule is defined by lambda. So, you have to be at least in multiples of this lambda, okay. You cannot be less than that. So, these are the steps for the mask generation that we already have discussed. So, this is just a pictorial view. So, you have a p type semiconductor, on top of it you grow oxide, then you have a poly. So, these are the steps, right. So, then you use some UV light to harden the coating, right, and you do the corresponding doping. Okay. So, if you see this previous one, so this is your oxide, this is your poly, and on top of it another layer is there. Now, what you are doing? You want to make your gate oxide in this region. So, other regions are hardened, right, and then you are doing the etching. So, in this region it will be etched. So, you see only this structure remains. So, this is the process. Then what will happen? So, up to this you see you have a p substrate and then oxide is grown and other oxide area are etched out, and then on top of this you have a poly region, right. So, these are now open. Now, what you will do? Then what is your structure for source and drain, that portion you will do the doping, right. So, if it is a ion implantation, some accelerated ions will be passed through it. So, some accelerated donor atoms will be passed through it, okay. And the regions you do not want, you will block that regions, right. So, what will happen? So, depending on the accelerations and certain criterias, how much depth you will be having of this diffusion, that will be decided, and you will be having the N plus region source and drain ready, right. So, up to this is that. Then what you are doing? You are again growing some oxide layer on top of it. So, this is again some oxide layer, okay. And where you want to have the metal connections, there you are creating some window and you are doing the metal interconnect, okay. So, for this example this is short, if you do not want then there will be some disconnect here, right. So, for this example they have made like that. So, that is the step by step how you are progressing, right. So, when this is done, this source metal connect and drain metal connect is done, you will get a this kind of window and structure, right. So, this is your source diffusion, this is your drain diffusion, this is your gate, this is your metal 1, this is your metal 1. So, this will be your final structure will look like this. Okay. One extra step they have not shown, that is the some substrate connections would be also there. So, it will be something like this. So, what is substrate? Substrate is P, right. So, it could be P plus plus and this will be your metal 1 window. Okay. So, when you have a say this is your metal 1 and you can connect it to ground, that should be the design. Suppose you want to short it with the source. So, what you will do? You will extend this metal 1. So, it will get a short with this ground, right. Suppose you want to connect this to VDD. So, what you will do? You will take this and you will connect to the VDD. Okay. So, that is why you will be doing the layout. So, this is just a quick example, and so the PMOS will be also similar, only what difference? Only one extra layer will be there, that is this NOL. So, you see previous structure, if you see there was no surrounding mask, right, but here you need a. So, one NOL mask will be there, you need to click that and need to enclose your MOS structure PMOS. Okay. So, this total PMOS, actually this total PMOS is in NOL, right. So, you have to cover full PMOS structure, understood. So, same way then you will be having the connections for the gate, drain, and again for similarly the NOL contact also not given here. So, what you need? You need to extend it little bit and some NOL tab, N tab generally the name is in tap or in contact. Okay. So, technology different name could be there. So, you need to put this as a contact for the NOL and connect it to VDD, right. Now, after this we need to discuss about the packaging. Okay. Packaging, if you have the experience of doing the lab, you will be seeing that in lab most of the popular material are generally DIP package or ceramic package, right. So, generally popular body are ceramic or polymer plastics. So, inside if you open the case you can see the die or the chip and then you will be having the connection with the pin of the package. Okay. From the pin you will be having the connect to the IO pad of the die. So, these are different type of package materials. So, most low cost and for simpler applications we have DIP package, that is dual in line package, where on the both side of the IC we have the pins, right. And we can have other two. In this DIP package you can understand that pin density is less, right, all the pin are taking much area. So, if you want to increase your number of pin, then the DIP package is not suitable. So, in that case we generally go for ball grid array or pin grid array or PLCC or other leadless structure. Okay. So, this grid array, this pin grid array or leadless PLCC structure, these are for larger number of pin density. These are some connections technique for on the PCB, on the board, right, printed circuit board. For connections we can have through hole mounting, where this from the top and bottom it will be through hole and some copper connections will be there. So, if you place the, suppose for example, this is a you can think of a resistor. So, it will be connected here and you will be soldering this so that is very it is rigidly connected here, as well as the electrical connection is also maintained because of this soldering. And for modern devices, we can have a surface mount devices, that is known as the SMD devices. Okay. Surface mount devices, generally our packing density is quite high. Okay. This through hole, they takes, again it is limited by this area of this hole, and this SMD are very small. So, SMD cap or SMD resistor, they take very small area compared to this ceramic resistor or capacitor. Okay. So, we can have this surface mount and we can just solder them directly on the board. Okay. So, if we think about the what the extra thing that the modern technologies are providing. So, modern technology, apart from this normal description of whatever we have gone through, to have the better performance, they have little bit of modification sometimes. For example, they can have a LDD, that is lightly doped drain. Okay. So, what they will do actually, this drain region, this drain region will be covered by extra another layer lightly doped. So, this is, if this is N plus plus, sorry, this is P. So, if this is N plus plus, you will be having N or N plus. Okay. So, depending on this, its density will be little bit less. So, this kind of structure sometimes it can help in opposing certain kind of short channel effects, that we will when we will be discussing the short channel effects, we will discuss these techniques. So, there are certain, sometimes a field oxide is grown around some regions, some trench is used. So, this kind of different techniques are used to improve the performance. Generally, we used some better interconnects and low dielectric constant material, and sometime we cover the poly with silicide. Silicide is a particular coating which can improve your gate resistance. Okay. So, some regions, if you this silicide coating, it can change the resistance of this material. Okay. So, better interconnect, previously aluminum was used. So, copper is nowadays used for CMOS technology, and it has certain advantage. Its resistivity is lower than the aluminum. So, it acts as a better interconnect. It has certain disadvantage, but nowadays other techniques are invented to overcome those problems. These copper are coated with certain materials to stop the diffusion, easy diffusion into the silicon. Okay. So, this better interconnect that reduces the resistivity and your overall performance is improved. Similarly, some lower dielectric constant material are used, so that your capacitance is, effective parasitic capacitance is less. Okay. So, the technology is evolving like this. So, better interconnect, better metal lines and better lower dielectric constants are few among them. Another technology that we already discussed, that is SOI technology. So, it has certain advantage. One, we already discussed that parasitic will be less, right. So, we can see that a performance improvement of roughly 22% can be seen in SOI technology. Okay. So, what is happening here? So, you have a thick layer of SiO2, on top of it your design is there. So, this N plus source region, drain region is grown over a buried oxide, right. So, what it is doing actually, it is reducing your parasitics, and as you can understand that the substrate leakage is much reduced. The reverse bias diode, the PN diode that was forming between the substrate and the source region and the drain region, that is not, you cannot find it there. So, it has better on off characteristics. Okay. So, this is the advantage of the SOI technology, only disadvantage is the. So, the structure that we have discussed. So, when we for easy or first time drawing, we generally use a simplistic form of diagram that is known as the stick diagram. Okay. So, for example, when the designer is starting, so this is one easiest representation, so that you can roughly guess what should be your structure or how you can place them. So, this gives you a most easiest way of representing the layout structure. So, what you will do? You will be either use different colors for different metal or junctions or different shading technique. Okay. For example, here this different color is used for metal 2, for metal 1 another color is used. Okay. For contact some boundary is used, right. For poly and diffusion some other colors are used. So, this kind of way you can draw your transistors and can have the understanding that how your connections could be done. Okay. So, this is a example of a stick diagram, where this upper line is, this is of different color. So, in this picture it is not visible. So, this is your VDD line, this is your PMOS, this is lower one is your NMOS, right. So, this is the gate of the PMOS, this is the gate of the NMOS, they are sorted to input, right. This is an inverter, right. If you see this, you can understand this is the inverter, this is the PMOS, this is the NMOS, and their drains are sorted to the output and its source is connected to ground, its source is sorted to VDD, right. So, this is the easiest implementation. Now, these are few example, but this is not realistic, and so only on pen and paper it is okay, but on the tool this stick diagram is not that much popular, rather than we follow the modern. If you open the cadence, you will have the normal layout technique. So, this stick diagram is not that much popular, but for simplicity still the technique is taught in academics. So, that you can, if you have a complex structure or to start with, you can quickly draw and have an idea. Okay. So, that is the reason that we still teach the stick diagram, so that you have a basic understanding and you can represent any layout easily using this diagram. Okay. So, what they offer, the stick diagram, simultaneously they capture the circuit topology, they will provide you what are the interconnections and the geometry also, and this is compact. For digital circuit, they will be all the transistor will be operating as switches, and simple RC based tau can be used for timing analysis to generate the timing models and calculate the delay of the wires, right. These are the design rule check that we just roughly discussed, that there are certain rules that you need to satisfy before you can pass your layout. Okay. So, the first, your layout should pass all the DRC errors, what are the minimum distance between the certain materials, minimum thickness, all these kind of rules you have to satisfy, and then what the next step is to match your layout with your schematic. Now, your design could be error free, but there could be, suppose some connection could be wrong. So, schematic wise it may not be matched. So, next step is to do the layout versus schematic matching. Okay. So, first step is to pass all the errors, that is DRC rule you need to pass, and second is to you need to match your layout with your schematic. Okay. So, in case of digital design, all these layout are automated, but in case of analog design, generally most of the time it is hand drawn, because analog your number of transistors are less, but the circuit can ask for higher linearity and careful matching. So, generally all the analog layout they are hand drawn, but because in digital circuit your number of transistor is so large, you manually cannot do. So, we get the help of the tools. Okay. So, these are the design rule check, where we have certain rules like what should be the distance between the two contact, what distance should be between one poly to second poly, okay, what should be the minimum distance between one metal to other metal. So, this kind of certain rules are there that you need to pass. So, otherwise what will happen, suppose you have a thickness, suppose one metal line is very thick and another metal line is very thin and they are drawn very close. So, what may happen that it can get short, right, because when you are drawing this metal line, it is very difficult to control the width of this diffusion, metal diffusion, right. So, if it get enlarged somewhere, then it can get short, right. So, these rules ensures that your design is not wasted. Okay. So, these are the minimum safe distance they have calculated based on repeated fabrications, and they follows those minimum rule check. So, that we have discussed several time, and we have functional verification at each step, that also we discussed. So, we will be having functional verification, logic verification, circuit verification and physical design verification, and as we know that each level we should do a check that is it satisfying our target specification. Otherwise, what will happen, if you think that at the end you will do the final checking, that time much of time can be wasted. So, each steps you should have a verification, if it is working then you only go to the next level. This is the Y chart between the structural, behavioral and geometric layout design, and from system level to cell level all the connections are drawn like that. Okay. At the very basic level we have the transistor and we are going to the full system. So, these are few of the metrics, or you can have some trade off. There you will be always finding that they will fight each other. If you want better performance, your cost will go up. Okay. If you want low cost, you have to sacrifice some of the performances. So, there will be always some trade off and they can be fight each other. Okay. Between power, between area, between cost, between noise figure, so many things are interconnected that it is very difficult to. So, you need to find the what you want or what the designer want or what the end application is, and accordingly you have to select your architecture. Okay. So, you should select your architecture for your target, and that could vary widely. Okay. And this is why CMOS technology is preferred. So, I hope you all know the certain reasons. Can you tell me why CMOS is so popular? Power dissipation, static power dissipation is quite less, that we discussed, and also packing density is quite high. Okay. So, for digital design, this CMOS technology is very much suitable. Okay. Why? Because in CMOS what we have seen, complementary, each gate is made up of PMOS and NMOS. So, if one is on, other is by default off, right. So, we do not have low static power, that advantage we are having, right. Now, for analog design, previously in even few decades ago, this bipolar technology or BiCMOS technology was preferred because BJT, bipolar technology, they offers higher frequency. Okay. The bipolar technology is robust. Okay. And for analog design, as we need better linearity, So, for analog design this CMOS or bipolar technology was preferred, but with the invention and development of the CMOS technology, now it is also possible to make the both analog and digital on the same die. So, it is known as the SoC, system on chip. So, previous technology if you see that microprocessor is in CMOS technology, but if you have any analog block or module, they used to prefer the bipolar technology, but nowadays as CMOS is become quite mature and it is also offering quite reasonable performance for the analog circuits also. So, nowadays we will be seeing that most of the SoCs they are made up in CMOS technology. So, modern lower technologies they are more suitable for the digital designs, but if you see 180 nanometer, 250, so they are still quite good for the analog design also. Okay. So, this CMOS technology rapidly captured the digital market and this power dissipation is one reason. So, as I said that bipolar or gallium arsenide their speed is quite high, but for digital this CMOS quickly and this for because of another reason is lower fabrication cost. For this CMOS or bipolar or gallium arsenide their fabrication cost is also higher. Okay. And as CMOS technology is developed, it is now also suitable for the analog design also. So, one of the main reason is the low cost, that is the designer go for the CMOS. Okay. And why integrated circuit, I hope also you can answer that question also, that you can have high packing density. If you think of all the discrete element and the previous system on board. So, from system on board to we have moved to system on chip, right. So, this is the advantage that we have moved to integrated circuit, and for analog and digital or mixed signal integrated circuits have millions of transistors and the area is also low. So, we have lot of advantage in the all the portable devices. Okay, students. So, we will start a new chapter, that is the MOS device structure, geometry of the MOS and the current equations. So, we will quickly follow the semiconductor PN junction device structure, diode model, and then we will get into MOS structure. So, I hope you all can remember this p type semiconductor. So, in silicon we have valency of 4, right. So, when we dope with trivalent material having 3 valency, so we are having a vacuum, right. So, one hole is created because all the adjacent atoms are silicon. So, they need on the outermost orbit to make it neutral you need 8, right. So, 4 will each silicon will share with other 4 adjacent atoms to achieve the outermost orbit 8 electron, right. So, when one silicon is misplaced by a trivalent material, that is boron, so that particular connections will be having a one mismatch or one vacancy of the electron. So, that we termed as the hole, and so we can tell that if we have a trivalent doping, then majority of the carrier will be hole, right. So, we all know these basics. Similarly, if we the doping is pentavalent material, for example, phosphorus, then the opposite thing will happen. After making the 4 covalence bond, we will be having one extra electron. So, that will be our free electron. So, we can tell that for n type material our majority of the carriers are electron, right. So, on top of that, if our temperature is increased, device say collision is increased, then other free electrons will be generated, right. These are free electrons. On top of it, if temperature is increased, some of the covalence bond may break and few other free electron can join, right. So, these are the reasons that at higher temperature we have more number of free carriers. Okay. So, these are the basic things to have the N type and P type semiconductor structure. Okay. And this is our diode structure. So, we have P type material and N type material, anode and cathode, and this is our device structure. Okay. This is our P material, this is our N material, and these are our contact. Contact is just like we discussed, whatever the metal deposition and contacts, the same thing is there, and in between we can have a barrier, that is SiO2. So, this barrier potential we are not discussing, I hope you all know this. So, we are not getting into the barrier potential. So, let us just see the diode capacitance. Okay. So, sometimes what happens, this diode junction, and in reverse bias also you can see that this is a space charge region, right. There is no free carriers here, only the these are what? These are immovable ions, right. So, if you see this structure, this is your atom, right. So, if you remove this free electron, it becomes a ion, right, and as they are heavy, they cannot move. This free electron and hole, they can move, right, but these are having the neutron and the heavy. So, in this space charge region, if we have no connections and open circuit, and so what will happen, all the free electron and hole, they will combine and vanish, right. So, what remains then, if the free carriers are vanished, then there is nothing to neutralize these ions, right. So, it will be immovable ions. So, this space charge region, now you can see, think like that, this is one metal plate, this is another metal plate, and this is the dielectric material in between, is not it. So, a reverse bias diode, this you can think like that, suppose this is reverse biased. So, this will be one plate and this will be another plate, and in between the space charge region is behaving like the dielectric constant, all right. So, this reverse bias diode can behave like a capacitance, may not be a linear capacitance, but ideally it is behaving like a capacitance, right. Now, capacitance, you know what is the equation for capacitance, C is equal to epsilon A by say D or T, whatever. Now, this is C is inversely proportional this T. So, if T is more, your cap value will be less, and if T is small, your cap value will be. So, now you think, if you can control the reverse bias voltage, so what will happen, this width, that will change, and accordingly your capacitance will also change, right. So, you think of a modulation, you are giving a reverse bias voltage that is modulating your space charge region or depletion region width, and that is in effect changing your reverse bias capacitance. So, that way generally in communications technology, they use this kind of varactor diode, right. So, they use this diode in reverse bias as a capacitance to model, tune the circuit. Okay. So, this becomes, so you can see that your Cj is now variable, and you can control using a reverse bias potential, and certain you can design up to a certain value. So, that at that particular value it is tuned to your circuit or your frequency. Okay. So, these are certain applications for this reverse bias capacitance. The same concept you can also use in the MOSFET also. Okay. So, that was our diode. Now, let us come to MOSFET, and I hope you all know the symbol. So, there are several symbols. So, For digital circuit this symbol is quite popular, the NMOS is without any bubble and for PMOS there is a bubble at the gate, or we are having a arrow. Okay. For NMOS from the channel towards the source, this is the arrow, and for PMOS towards the channel. Okay. We have a fourth terminal, that is bulk terminal. Sometimes we use arrow for this bulk terminal, or sometimes we use without any arrow. Okay. Now, we already discussed that in digital circuit our MOSFET will behave just like a switch. So, what it will be? Either it will be connected to VDD or it will be connected to ground, and this will be controlled by a input and their drain will be sorted to output. So, all the digital logic, your MOS transistor is nothing but a off or a linear on in linear region. Why linear region? We already discussed. If you forget, just let us see. This is our linear region, right. So, here you see this is our ID, this is our VDS. So, here you see del V is quite large, del ID is ideally 0. So, it gives us a infinite resistance. So, in saturation we do not prefer our digital logic. Why? Because then the lot of loss will happen on the switch resistance, right. We want our R on to be ideally 0, it should be just on and off. Okay. So, this is not preferred for digital design, but this is preferred for digital design. So, simple. So, if we provide a 1 at the NMOS, it is on, if we provide a 0 at the PMOS, it is on. And substrate, you all know, NMOS substrate should be sorted to ground, PMOS substrate should be sorted to VDD. Why? Because to make the substrate PN junction diode reverse biased, right. So, this is a structure that we were discussing in the layout structure. So, this is our 3D view. So, this is our gate, this is our L and this is our W. Okay. So, we last day also we discussed that effective length is less than the drawn length, right. So, L effective is equal to L drawn minus twice of LD. LD is the diffusion. The source and drain region, it is very difficult to control the diffusion. Sometimes this diffusion extended inside the channel. So, effective length will be little bit reduced, and this is the NMOS and PMOS both, and this is the formation of the depletion region. Now, we are getting into how the MOSFET is working. Okay. So, let us think that first that source and drain both are sorted to ground. So, there is no potential at the source, only you are giving some potential at the gate. So, first tell me what will happen if I give a positive potential at the gate and this substrate is P substrate. What are the majority carriers in the P substrate? Holes. So, if you have a positive voltage at the gate, all these holes will feel what? A repulsion, right. So, all of these holes will move away from the channel, right. So, what will remain there? Immovable ions. If you remove the holes, then the atom becomes an ion, right, because there is no one to balance the ion, right. So, what will happen if you remove the holes? What will be the ions charge of the ions? Negative. Okay. So, what will happen? One depletion region or space charge region will be formed. This is the first step. Okay. So, what is the first step? You see, source and drain are both ground, no lateral potential, only vertical field is there. vertically I am connected a positive voltage at the gate, what it does? It repels all the holes. So, now a space charge region is formed. Now, can you see that what it will behave like? This gate is a, you can think of a one plate of the capacitor, there is a gate oxide, on top of it you have a space charge region, then you have a substrate, substrate will behave as the other plate. So, between gate and channel, gate and bulk, you will be having a capacitance, right. Total capacitance will be COX into W into L area, right. Okay, roughly. Next step. Now, suppose you start to improve your this gate voltage. Okay. Now, what you are doing? You are starting to slowly building up the gate voltage. So, what will happen now? The vertical field is increasing, right, field strength is increasing, right. So, if you have a positive voltage and what are the N regions, source and drain regions, they are N plus. N plus means majority carriers are electrons. So, you think two different way you can think. One is you are increasing your positive potential. So, the positive charges at the gate terminal will keep on increasing, building up, right. So, similarly what will happen, your negative, this negative ions, suppose there are 4 negative ions. So, initially you have 4 positive charge on the gate plate. Now, suppose you are again increasing your field, okay. So, more plus charge are coming. Now, you need in the opposite plate you need same number of charge, right. So, this high field what it will do? It will attract the electrons from the nearest region, because nearest regions they are a like a pool of electron. So, this electron they will feel a attraction towards this vertical field, right. So, what will happen? Few electrons will start to get inside the channel, right, and now they will come up and will balance the total number of charge plus and minus. Now, see in this P substrate your majority carrier was holes. Now, because of this incident, now what happens? Your channel is just started to, we call it inversion, channel is inverted, clear. Previously my channel material was P type, but because of this positive voltage what happens now? Negative charge comes from the source and drain region and say pools of electrons forms. Now, if you do a positive voltage at the drain, what will happen? Electrons will, they will be attracted. So, you will be having a connections. Any question? These steps are clear. That is this threshold voltage, right. So, when you have a see this total charge, this is the total charge of this space charge region. Okay. This depends on the Fermi level and the work function difference between this poly and this region. Okay. So, when you are having this threshold voltage, so this threshold voltage it is just at the onset of starting inversion. So, up to this point it is only the space charge region. Now, what happens if you increase this voltage further, this voltage, if your gate voltage is above this VTH. Okay. So, when your VGS is equal to just VTH, you are up to space charge region, but if your VGS is above VTH, that we call the overdrive voltage, then as if we can think of a up to VTH it is, you can think of a 0, then it is the delta, that is excess voltage. That excess voltage will, that is the difference above the work function difference, and that is pulling the electrons from the source region. So, you think like that way, that as the gate voltage is getting more positive, the electrons feels lot of, the vertical field is so strong that it comes out of its region. Okay. So, this is the definition of the threshold voltage, and if we see the pictorial view how the steps are happening. So, first we have the space charge region, and that time it is behaving like a cap, and now even if we keep on increasing our gate voltage. So, the number of positive charges at the gate terminal is increased. So, that to balance that, in spite of this space charge region, space charge negative immovable ions, we also need additional electrons, clear, because its voltage is now such a high. Okay. So, as if you think that it is pulling all these electrons, clear, and now what happens, a channel is formed. Now, if we add a positive voltage at the drain region, so this positive field will attract all this electron, and there will be a constant connections of flow of current. The things will be just opposite for case of PMOS. We will discuss this in next class.